Jianan Li will talk about probing the physical conditions of the interstellar medium in the most distant quasar host galaxies.
So can you see my screen and can you hear me?
Yes, both. Excellent.
Okay. So hello everyone, I'm Jianan Li, a graduate student from Peking University in China. And today I'll talk about the molecular, ionized, and atomic interstellar medium in a particular redshift 6 quasar, the SDSS J2310. So we have already know that observations of the quasars at the highest redshift are essential for our understanding of the coevolution between the supermassive black holes and the host galaxies, especially the observations of the interstellar medium at redshift 6, because the interstellar medium are directly exposed to the radiation field of both the UV photons from star formation and the radiation field produced by the very luminous quasars. So studying the physical conditions of this interstellar medium will also help on our understanding of the coevolution. So these studies are basically through observations of the CNO fine structure lines and also the submillimeter CO transition lines. And these lines are easily accessible by ALMA, NOEMA, and VLA at redshift 6. And through these observations, our objectives are to find if there is a typical SM physical conditions for this redshift 6 quasars and how is it compared to local starburst systems and AGNs. And also, are we able to discriminate between different ISM heating mechanisms, like the UV heating, which is produced by the stars, and S3 heating, which is mainly produced by the AGNs. So then we start a case study of one of the far infrared brightest quasar, J2310 at redshift 6. So this quasar is very interesting, and it has been detected in the low CO transition to mid-J CO transitions, and the C+ line, and also the oxygen 388 micron. So in this talk, I will briefly introduce our ALMA and NOEMA observations of the molecular CO lines and water emissions, and this has been published in Li 2020, and we also include the fine structure line observations, and this is our ongoing work. So actually, our new CO observations are covering J equals 5 to 13, and in complemented with previous CO2-1 data, we are actually probing the CO from J equals 2 to 13. So now I will introduce the physical conditions of the molecular gas probed by the CO SLED analysis. So the CO spectral line energy distribution is shown in this plot. So it's the CO flux as a function of the rotation quantum number J. So this shape of the CO SLED change with both different density for fixed temperature and also different temperature for fixed density. So these are ideal probe of the temperature and density of the molecular gas. So currently, there are only 4 published CO slides for redshift 6 quasars with at least 4 transitions, so which enable us to do the CO slide analysis. And the above 3 panels are result from previous work, and this is our result for this J2310 quasar. So if we use one gas component to feed the data, we get a warm and dense gas component with temperature of around 228 Kelvin and molecular hydrogen density of 10 to the 4.75 per cubic centimeter. And if we use 2 models to feed the data, we get a cold component in blue with a temperature of 50 Kelvin and a warm component with a temperature of around 300 Kelvin. So we find that all these different quasars with CO slide detections have different shapes of the CO slide. But it seems to be there is a universal warm and dense component which dominate at the high J CO transitions. So what is the heating mechanism of this highly excited CO component? We then compare the CO slide of this quasar in black with the local LIRG and starburst galaxies, and also the high redshift submillimeter galaxies. we find that this quasar show high CO excitation at J equals 8 and above compared to these starburst systems. And we also compare this quasar with local representative starburst galaxy and AGNs. We find also that higher CO excitation for this quasar compared to the local examples. And here is the SLED comparison with other redshift 6 quasars and also the redshift 224 length quasars. We find that this quasar has a SLED among this high redshift and length quasars. So the high CO excitation compared to the local and high redshift starburst systems may reflect that there are other mechanisms besides the UV heating from young massive stars. Maybe the AGN also contributes to the heating to the molecular ISM. And then I will introduce the neutron and ionized ISM observations. That there are many observations of the nitrogen-2 122 micron and also the oxygen-1 150 and 46 micron, which probe the neutron gas and the ionized gas. So the y-axis is the line to far infrared ratio, and the axis include the far infrared luminosity for these two panels and the far infrared surface brightness for these lower two panels. So for the nitrogen-2 line, this dots with no error bars are local dwarf galaxies, LIRGs, star-forming galaxies, and AGNs. And this with error bars are high redshift submillimeter galaxies and quasars. And so this quasar generally follow the trend of the local relation. And also we find that in the far infrared surface brightness plot, all of these high redshift objects lie within the deficit trend of the nitrogen-2 to far infrared ratio. As for the oxygen-1 line, this is the far infrared surface brightness. We find that all of these high redshift objects are above the relation set by the local samples. So this suggests that we actually find similar line deficit trend in the nitrogen-2 line, but there's no sign of oxygen-1 deficit. And from our new observations of the ionized and neutron gas complemented with previous C+ and oxygen-3 line, we are able to use these line ratios to probe the physical conditions of the neutron and ionized gas. So this plot, the y-axis shows the luminosity ratio of the C2 to oxygen-1 line, and the x-axis is the oxygen-3 to nitrogen-2 line. So for the C2 to oxygen-3 ratio, we find that this quasar together with other two high redshift objects lie on the lowest C2 to O1 ratio compared to the comparison samples. And the low C2 to O1 ratio are indicator of warm and dense gas. This together with the very high oxygen-1 to far infrared ratio in this quasar suggests that the high warm and dense gas may be heated by the AGN. And here is the oxygen-3 to oxygen-1 line. This is a proxy of the ionized to neutron gas volume filling factor. So we find that this quasar has a lower volume filling factor, ionized volume filling factor compared to the mean of the local sample and also compared to other two high redshift objects. And as for the oxygen-3 to nitrogen-2 ratio, we find that this quasar shows a comparable ratio with the mean of the local sample, and this is smaller than the other two high redshift objects. And from the nitrogen-2 line, we also derive that less than 17% of the C+ is from the ionized gas region. So this is also in agreement with the lower ionized gas fraction derived from the line ratio analysis. And because the oxygen-3 to nitrogen-2 line has a dependency on the metallicity. So this line can be used to estimate the metallicity. And from these two luminosities, we derive a metallicity of 0.5 to 2 times of the solar luminosity. This means that this redshift 6 quasar is already metal enriched with solar metallicity. And we also use this line luminosities to derive the star formation rate. And we find that except for this oxygen 1 line, the other lines have a reasonable estimation of the star formation rate. So here comes the summary. So our SLED analysis suggests the gas is dominated by a warm and dense component, and this is very universal for the redshift 6 quasars with SLED detection. And these are probably signs of the AGN heating to the gas. And comparison of this quasar with other high redshift starbursts and local AGNs suggests higher CO excitation. But this high CO excitation is also found in other redshift 6 quasars and lensed quasars. And through the fine structure line ratio analysis, we find a low C2 to O1 ratio together with the high oxygen 1 to 5 infrared ratio reveal a warm dense gas is likely a result of AGN heating to the SM. And this oxygen 3 to oxygen 1 ratio show a smaller ionized gas fraction. And the oxygen 3 to nitrogen 2 line indicate solar metallicity of this quasar redshift 6. So I'll stop here and take questions. Thanks.
Thanks, Jianan, for a nice talk. We've time for very few questions. So one question is, do you think the CMB has any effect on the line ratios seen?
Oh, so the CMB?
Yeah, the CMB.
Actually, the CMB has some impact on the CO lines because actually I have read the impact of the CMB. It has only it only affects the very low frequency lines like the CO221. But from the modeling, we actually consider the CMB effect into it. So it has no influence to the CO SLED. However, for the fine structure lines, I don't think the CMB have a very large impact on that, because the CMB only has temperature of 20 Kelvin. However, the excitation temperature of these fine structure lines are usually several hundred Kelvin.
Okay. Some more questions. So why is the O1 derived star formation rate an outlier?
Actually, I have shown that from the oxygen 1, the C2 to oxygen 1 ratio, we find it is not comparable to the local samples. It is lower, which means the gas is warm. And also we find high oxygen 1 to 5 infrared ratio, which may be also the extra oxygen 1 emission is likely a result of other heating mechanism in addition to the UV photons from star formation. So it's likely that this high O1 luminosity has a contribution from AGN heating. So because this star formation rate are based on the assumption that all of these lines trace the far UV photons from star formation, so they can use to derive the star formation rate. If there is a significant contribution of the O1 to of the AGN to the O1 line, then this line will be an outlier. So this is also consistent with what we find in the line ratio and also in the oxygen 1 to 5 infrared ratio.
Okay. And then final question, would it be possible to carry out an analysis of the XDR versus the PDR and possible shock models contribution to the excitation of the different CO lines?
I think currently it's not possible for the high redshift 6 quasars because these quasars are not many of them have been detected in many CO transitions. So if we want to discriminate between the SDR and the PDR and also shock model, we need many CO detections, especially for the very high J part and also for the very low J part. So for these quasars, actually, we see that we only detect one of the low J CO, which constrain the PDR, And maybe in the middle, there's contribution from both components. However, for the high J, we only have 13 to 12. So I think this kind of analysis would be possible for the local AGNs, but currently it will not be possible for these high redshift quasars.